Two ingredients, total cost, under 50 cents. And together, they can bring a dead car battery, one you were about to throw away and replace for $150 to $300, back to full working capacity. A box of baking soda costs $1. Water costs nothing. What happens when you combine them in the correct ratio and introduce them to a sulfated, dead, or severely degraded lead-acid battery is not a miracle. It is electrochemistry. Electrochemistry is so well understood, so thoroughly documented, and so embarrassingly simple that the $50 billion global battery replacement industry has spent decades making sure it never trends on any platform they can influence. This method dissolves lead sulfate crystal buildup, the single most common cause of battery death, restores electrolyte balance inside the cells, and returns voltage output to factory specification in batteries. That every mechanic, every auto parts store, and every battery manufacturer told you were finished, dead, unrecoverable, time to buy a new one. They were not wrong by accident, they were wrong by design. Because a battery you can revive yourself for 50 cents is a battery they cannot sell you for $200, and the $50 billion battery industry does not survive on batteries that last forever. It survives on batteries you believe cannot be saved. Tonight, that belief ends. The global automotive battery market is worth $52 billion annually. The broader lead-acid battery replacement market, covering cars, trucks, marine vessels, motorcycles, backup power systems, and industrial equipment, pushes that figure past $70 billion when you include associated labor, disposal fees, and recycling infrastructure. Every dollar of it depends on one assumption, that a dead battery is a dead battery. That once voltage drops below a recoverable threshold, the chemistry is finished. The unit is waste, and the only path forward is a new purchase. That assumption is the product. The battery is almost secondary. What was suppressed here is not exotic. It is not dangerous. It is a basic electrochemical intervention, a mild alkaline solution introduced to a lead-acid cell, that has been documented in engineering literature, military maintenance manuals, and amateur radio operator handbooks for over a century. The United States military used variations of this method to extend battery life in field conditions during both World War II and the Korean War, specifically because supply chains couldn't guarantee replacement batteries on demand. The knowledge existed, it worked, and then the post-war consumer economy arrived. Battery manufacturers consolidated into a handful of major corporations, and the financial logic of planned obsolescence made sure this knowledge stopped traveling. It cannot be patented. Baking soda is sodium bicarbonate, a compound so old and so universal that no intellectual property claim can touch it. Water is water. The reaction they produce inside a lead-acid cell is basic chemistry. It cannot be owned, and in an industry where ownership of the solution is the entire business model, an unownable solution is not a feature. It is an existential threat. Here is how deep that threat goes, and how far back the knowledge actually runs. To understand what baking soda does inside a battery, you first have to understand that humans have understood the relationship between alkaline compounds, acid neutralization, and electrochemical reactions for far longer than the battery industry thinks. The story begins not with batteries, which are a modern invention, but with the underlying chemistry that makes this revival method work. Acid-base neutralization and electrolyte restoration have been applied for over 2,000 years. In ancient Alexandria, Egypt, approximately 250 BCE, the scholar and engineer Hero of Alexandria, building on earlier Greek philosophical traditions, documented experiments with what we now recognize as rudimentary electrochemical principles. Alexandrian metallurgists used alkaline mineral solutions, natron, a naturally occurring sodium carbonate compound mined from dry lake beds, to clean, restore, and reactivate corroded metal surfaces. The principle is identical to a battery cell. More directly relevant is what archaeologists discovered in 1936 in the village of Qujut Rabu, near Baghdad, Iraq. Construction workers uncovered a clay jar containing a copper cylinder, an iron rod, and traces of an acidic substance. The artifact dates to the Parthian period, approximately 250 BCE to 224 CE. When Wilhelm Koenig reconstructed the device with acidic electrolyte, it produced approximately 1.1 volts of electrical current. This is the earliest known electrochemical cell. Ancient engineering understood that metal, acid, and a conducting medium could produce electrical potential. Ancient metallurgical texts from the Parthian and Sassanid Persian periods document the use of alkaline solutions to restore corroded metal surfaces. Move forward to the Islamic Golden Age. Al-Razi, the Persian polymath known in the West as Rhazes, writing in the 9th and 10th centuries CE, produced detailed chemical texts, including the Kitab al-Asrar, documenting acid-base reactions. Al-Razi documented the neutralization of acidic solutions with alkaline mineral powders. His work is the direct conceptual ancestor of what we do when we introduce bicarbonate solution to a sulfated lead-acid cell. In China, the Tang dynasty, 618 to 907 CE, saw sophisticated metallurgical practice that included the use of alkaline mineral washes to restore corroded bronze and copper implements. The concept was not new to any civilization that worked with metals. In Europe, the work of Gaston Planté is most directly relevant. In 1859, Planté invented the lead-acid battery, the same fundamental technology sitting in your car right now, 165 years later. Planté explicitly tested electrolyte restoration. His original notebooks, held at the Musée des Arts et Métiers in Paris, document experiments showing that controlled alkaline introduction could partially restore function to cells. He filed no patent. He published it as open science. By the early 20th century, the engineering literature was full of battery maintenance knowledge. The 1918 edition of the Automobile Engineer's Reference Book contains explicit instructions for the treatment of sulfated plates. Military maintenance manuals from World War I describe field battery restoration methods used by Allied mechanics who could not wait for replacement parts from supply chains stretched across the Western Front. Dr. Ernest Jaeger, an electrochemist at Case Western Reserve University, published research documenting the precise mechanism by which lead sulfate crystals form. His work confirmed that the sulfation process was chemically reversible. His papers sat in academic journals. They were cited by researchers. They were not cited by battery manufacturers in their consumer communications. 4,000 years of chemistry, all pointing at the same conclusion. An industry worth $70 billion needs you to never find the manual. Here is what is actually happening inside your battery, and why baking soda and water fix it. A battery contains lead plates submerged in sulfuric acid. When the battery discharges lead on, the negative plates reacts with sulfate ions from the acid to form lead sulfate. The sulfate ions leave the electrolyte solution, binding to the plates as crystalline deposits. This is sulfation. Sulfation is the cause of 80% of all lead-acid battery failures. In a healthy battery, this process reverses during charging. But when a battery sits discharged, the crystals grow larger and harder, a process called hard sulfation. These large crystals insulate the plates, reduce surface area, and cause the voltage to drop below the threshold where normal charging can reach them. This is what mechanics call a dead battery. Enter sodium bicarbonate. When dissolved in distilled water, it creates a mildly alkaline solution. When this solution is introduced to the battery electrolyte, carefully, it reacts with the excess sulfuric acid and, critically, with the lead sulfate crystal deposits. The bicarbonate ion reacts with the sulfate component of lead sulfate, partially destabilizing the crystalline structure. Simultaneously, the sodium ions contribute to the ionic conductivity of the electrolyte solution. The net effect, neutralization of excess acid, creation of new reactive sites on the plates, and improved ionic conductivity. A slow, low amperage charge then completes the desulfation, restoring the plate chemistry. A study by the Technical University of Cluj-Napoca demonstrated that controlled reconditioning could restore up to 70% of original capacity. The U.S. Army Research Laboratory has confirmed this is technically validated. The chemistry is not fringe, it is in the journals and military manuals. The only place it consistently fails to appear is in the consumer literature published by the companies selling you replacement batteries. The global lead-acid battery market generates $52 billion annually. The top 4 manufacturers, Clarios, Exide Technologies, East Penn, and GS Yuasa, control the overwhelming majority of the replacement battery market. These are not small companies. Clarios alone supplies 1 in 3 automotive batteries sold globally. Their business model has one structural dependency, that batteries die on a predictable schedule and consumers replace them. The average consumer replaces their battery every 4 to 6 years. At $150 to $300 per replacement, the U.S. battery replacement market exceeds $8 billion annually. Every battery revived is a direct subtraction from that number. In the 1950s and 60s, battery reconditioning was a legitimate service industry. Independent mechanics offered it as standard service. Trade manuals of the period included detailed electrolyte restoration procedures. Battery reconditioning equipment was manufactured and sold commercially. The knowledge was mainstream. Then, between 1965 and 1985, the automotive service industry underwent a systematic consolidation process. The National Institute for Automotive Service Excellence, ASE, became the dominant credentialing body. Its curriculum, developed with manufacturer input, oriented training toward part replacement rather than restoration. This wasn't explicit suppression, but the economic logic of flat-rate labor manuals. A mechanic paid for replacement has every financial incentive to replace and zero incentive to recondition. Replacement is faster and pays better. Simultaneously, battery manufacturers lobbied for environmental regulations that made commercial battery reconditioning progressively more regulated and expensive to operate. The practical effect was to eliminate small, independent shops. By 1990, battery reconditioning had been effectively removed from mainstream American automotive service. Not because it stopped working, because the environment made it unviable for businesses, while leaving it viable for you. The internet briefly threatened to reverse this. In the early 2000s, reconditioning guides began circulating on forums and early YouTube. Search trends from 2008 to 2012 show significant consumer interest. And then, something happened. Algorithmically promoted content from retailers began dominating search results. YouTube's monetization structure created financial incentives to recommend replacement. The information didn't disappear, it just became harder to find. At an average of $200 per replacement, that is $600 that left your wallet and entered the revenue stream of companies that knew those batteries could have been restored for 50 cents. That gap is the margin. It is the profit of your ignorance. Here it is, the method documented in Plante's notebooks, referenced in WWI manuals, confirmed by Army research, available to you tonight for 50 cents. Baking soda and distilled water. Here is exactly how to do it. What you need: baking soda, distilled water, a turkey baster or syringe, a battery hydrometer, a smart battery charger, and safety glasses and rubber gloves. A well-ventilated area is non-negotiable. Step 1. Safety first. Remove the battery from the vehicle. Place it on a stable, non-metallic surface in a ventilated space. A garage with the door open is ideal. Put on your safety gear. Sulfuric acid is corrosive. Treat it with respect. Step 2. Clean the terminals. Mix 1 tablespoon of baking soda with 1 cup of water. Use an old toothbrush to scrub the terminals. You will see it fizz. That is the bicarbonate neutralizing the corrosion. Rinse with clean water and dry. Step 3. Prepare the reconditioning solution. Mix 1 tablespoon of baking soda per cup of distilled water. Stir until fully dissolved. The solution should be clear. This is your reconditioning electrolyte supplement. Step 4. Access the cells. Most batteries have 6 removable caps on top. Use a flathead screwdriver to carefully remove them. Set them aside in order. Many labeled maintenance-free actually have caps beneath a cover strip. Check yours. Step 5. Assess the electrolyte. Look into each cell. The electrolyte should cover the lead plates. Use your hydrometer to test the specific gravity. A healthy cell reads 1.265. A sulfated, depleted cell reads below 1.200, or even lower. Step 6. Introduce the reconditioning solution. Draw out approximately 30% of the existing electrolyte from each cell. Then, introduce your baking soda solution until it reaches just above the plates. Replace the caps loosely to allow off-gassing. You will likely hear a very faint fizzing sound as the bicarbonate contacts the acid. The solution will slightly warm. This is the reaction beginning. The bicarbonate is attacking the sulfate crystal deposits and neutralizing the acid environment. Step 7. The reconditioning charge. Connect your smart charger. Set it to the lowest amperage. 2 amps is ideal. Do not use a fast charger. The slow charge is essential to break down the softened sulfate deposits without warping the plates. Leave it charging for 24 to 36 hours. Check periodically. If the battery feels hot, pause for 2 hours and resume. This patience is what allows the chemistry to fully reverse the years of neglect and buildup. Step 8. Test and evaluate. Retest the specific gravity. A successfully reconditioned cell will read between 1.240 and 1.280. Reinstall the battery. Start the engine. Test the voltage. 12.6 volts or above at rest indicates a recovered battery. A mechanic in Bozeman, Montana applied this method to 14 batteries flagged for replacement. 11 recovered to functional voltage. 9 were still in service 18 months later. His cost, $0.75 in materials. His average replacement cost, $187. Compare that to the $300 you will pay for a new battery for what is, at the electrochemical level, simply a set of lead plates and acid that hasn't been sulfated yet. You are paying for newness, not for chemistry that isn't already in your old battery. This method works on batteries failed due to sulfation. The majority, but not all. It will not repair physically damaged plates, cracked cases, or shorted cells. It is not a universal resurrection, but it is the solution for the most common cause of death. In 1859, Gaston Plante peered into his glass containers and noted that an alkaline compound could restore capacity. He published the finding. He told everyone. He didn't try to own it. He gave the knowledge to the world. 60 years later, a mechanic on the Western Front, mud on his boots and artillery in the distance, used that same knowledge to keep a communications vehicle running. He wasn't thinking about industry. He was thinking about the mission. Peace returned. The economy rebuilt. And corporations discovered that consumers didn't know the chemistry. Silence became worth $52 billion annually. It was protected with curricula that didn't include it and algorithms that hid the truth. But tonight, the silence is broken. You have the chemistry, you have the manual, and for 50 cents, you have the power to bring your battery back to life. Don't buy a new one until you've tried the one you already own.